any real-world problem that involves a rate of change, and they range from marginal cost in economics to objects in motion, including the position of planets in the solar system, can be represented by differential equations. The invention of differential equations enabled mathematicians to solve problems that had befuddled them for centuries. Hi, my name is Tom Atwater, and that's what we are going to investigate in today's lesson. Let's start with a definition. Definition of differential equations. An equation involving a derivative is called a differential equation. The order of a differential equation is the order of the highest derivative involved in the equation. Let's work an example of a differential equation. Find the general solution to the exact differential equation given by dy dx equals 5x to the fourth minus secant squared x. The solution to this particular problem is the antiderivative. And so what we're going to do is find the antiderivative of 5x to the fourth minus secant squared x. So let's do that now. That's going to give me y equals x raised to the power of 5, and that takes care of the coefficient 5 as well, so that's good. And then the antiderivative of secant squared x is tangent x. Then we have plus c, the constant, which takes into account whatever the initial possibility is for the initial conditions. Now, the general solution to a first-order differential equation is continuous. The only additional information needed to find a unique solution is the value of the function at a single point called the initial condition. A differential equation with an initial condition is called an initial value problem. It has a unique solution called the particular solution to the differential equation. Let's look at an example where we will find that particular solution. So find the particular solution to the equation dy dx equals 3 sine x and y equals 2 when x is equal to 0. So to do this problem, we start by finding the general solution. So let's do that. In other words, y is going to be equal to the antiderivative of 3 sine x. And the antiderivative of sine x is, of course, negative cosine x. So this would be negative 3 cosine x plus c. And what we know is y is equal to 2 when x is equal to 0. So what we have then is substituting those in, 2 equals negative 3 times the cosine of 0 plus c. The cosine of 0, remember, is 1. So what we have is 2 equals negative 3 plus c. That gives us a value for c of 5, which means we can now substitute that into the general solution, and it gives us a particular solution. So y equals negative 3 cosine x plus 5. And that gives us the particular solution when x is equal to 0 and y is equal to 2. Well, now it's time for you to try a problem. I would like you to find the particular solution to the equation du dx equals 7x to the 6th minus 3x squared plus 5, and u is equal to 1 when x is equal to 1. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Welcome back. Let's find out how you did on this problem. The first thing we need to do is find the antiderivative of the du dx problem. And so we would have u is equal to x to the 7 minus x cubed plus 5x plus c. And we know that u is equal to 1 when x is equal to 1. So we can plug in 1 for u and 1 for x. And that will allow us to solve for c, and we will find that c, in this particular case, we have 1 minus 1, which is, of course, 0. We subtract 5 from both sides, and we find that c is equal to -4. So now we can substitute that back into the general equation, and we get u equals x to the 7th minus x cubed plus 5x minus 4. And that would be the particular solution that you should have come up with on that particular problem. Okay, if a curve is continuous, the initial condition determines a particular solution for which the curve passes through the given point, and it pins down the solution on that entire continuous domain. However, if the curve is discontinuous, then the initial condition pins down only the continuous piece of the curve that passes through that given point, in which case the domain of the solution must be specified. Let's take a look at an example where we solve the initial value problem explicitly. dy dx is equal to -1 over x squared minus 3 over x to the 4th plus 12 when y is equal to 3, y is equal to 3 when x is equal to 1. So the point 1, 3, which is the point of the initial condition, pins down only the continuous piece over a certain interval. And that interval is going to be from 0 to 8. And so when we give our answer, we have to take that into account. So let's take a look at finding this antiderivative. Again, y is going to be equal to the -1 over x squared in terms of anti-differentiating it is 1 over x. Then we have plus 1 over x cubed plus 12x plus c. And again, we substitute in 3 for y and 1 for x. That allows us to calculate the value of c, and in this particular case, we will find c is equal to -11, which I can substitute back into my general solution and get the specific solution of y is equal to 1 over x plus 1 over x cubed plus 12x minus 11. And we have to specify that the domain is such that x is between 0 and infinity. And so we can find that is continuous 0 to infinity, but that we can't say what's happening in the other section that is less than 0, since that point only deals with the side greater where x is greater than 0. All right, that's great. Next, let's take a look at the fact that sometimes when you want to do an example, you might have to use the fundamental theorem of calculus to solve the initial value problem, because, remember, we might be unable to find the antiderivative. So let's take a look. Let's solve the initial value problem using the fundamental theorem, and we have dy dx is equal to the sine of x squared. Y is equal to 5 when x is equal to 1. So let's take a look at using the fundamental theorem for this. what we have then is, of course, that f of x is going to be equal to the integral from 1 to x of sine t squared dt plus our constant c. And what we know is that x is equal to 1, y is equal to 5. So f of 1 would be 5. And that's going to equal the integral from 1, and now we have to put a 1 up there because that's the value for x, of sine t squared dt plus c. Well, remembering that when you evaluate an integral and the interval, in this case from 1 to 1, in other words, the bounds are the same value, that integral is, of course, equal to 0. So therefore, we find that c is equal to 5. So our solution then, using the fundamental theorem of calculus, is this. And I just going to erase part of this to give me some more room. We get f of x is equal to the integral from 1 to x of sine t squared dt plus 5. And that's our particular solution to that particular problem, but we had to use the fundamental theorem of calculus to help us do that. Let's explore graphing the general solution to a differential equation. The general solution will always have that plus c, that constant added on as part of its function. And recall that when you graph y equals f of x plus c, it's simply the graph of y equals f of x shifted vertically by whatever the value c is. Since c is a variable, we can get what we call the graph of a family of functions. We can graph some of the functions that are part of the family just to illustrate this idea. So let's take a look, and let's say we want to graph the family of functions that solve the differential equation given by dy dx equals cosine of x. So let me look at this. Here's dy dx equals cosine x. Now we know that we can we can anti-differentiate that, and we will get the answer y equals the sine of x plus that constant. And if you were to plug these key presses into your calculator, this would give you a family of functions for this graph y equals sine of x plus c, because c, of course, is a variable. And let's take a look at what that graph would be. It would be the sine curve, which you might recognize this one here that I'll outline in red as the one that you typically draw, because that represents y equals sine x. And then every other one is simply, this would be sine of x plus 1, sine of x plus 2, sine of x plus 3. And down below, let's just take one example, this one here, that would be sine of x minus 3. So that's the graph for the family of functions that solves that differential equation. All right, next, let's take a look at constructing what's called a slope field for that same exact function, dy dx equals cosine x. A slope field is similar in that what it's going to do is find slopes at certain points. whereas your calculator just helped us get the smooth, continuous graph. What the slope field is going to be sections of it, and we can look at the slope field as a method for finding and then approximating what we think that the family of functions would look like. So what we have here is I'm picking certain values for x, ones that I know will fit well with what we're looking at. Now, we know that when we anti-differentiated, we had y was equal to the sine of x plus c. But a slope field, the slope, of course, is the derivative. So what we're going to look at actually is the values for dy dx equals cosine x. And so obviously we can't graph them all. That's why I've picked certain values. So for x equals to 0, we would find that we say y is going to be equal to the cosine of 0, which is going to be equal to 1. So what will happen is we will have tiny little segments at x equals 0 where we have a slope of 1. Okay? So these are going to be small little pieces of the linearization at that specific point. And of course, that's going to approximate what the whole curve will look like. And we're going to repeat the process. So let's take x equals plus or minus pi. So the cosine of pi and the cosine of negative pi are both equal to negative 1. So at pi and negative pi, we're going to have slopes of, or little segments with a slope of negative 1. What about now looking at x is equal to plus or minus pi over 2? In this particular case, plus or minus pi over 2 and odd multiples of plus or minus pi over 2, like plus or minus 3 pi over 2, will all give us a cosine equal to 0. So for all of those, we will have little segments with a slope of 0. And then finally, when we look at x equals plus or minus 2 pi, we come back to the fact that y is going to be equal to 1. And so let's take a look at what this slope field looks like when I take each of those and graph it onto the plane. So what we see are the examples of where we have a slope of 1, right? Which is where cosine of 0, x is equal to 0. Then we have slopes of negative 1 at our multiples of pi plus or minus pi, odd multiples. Then for plus or minus odd multiples of pi over 2, we have a slope of 0 here and here. And then finally, when we went to, and here's 3 pi over 2, so it's an odd multiple. And then finally, when we went to 2 pi, we said that the slope was back to 1. And so that's our slope field. And the idea is on this slope field that what we can do, let me erase those circles. The idea now is, to the best of your ability, to connect these linearizations like such. So again, you'll see that if I were to do that with all of these, we would get that graph of family of functions that we saw from the grapher when we plugged it in earlier in this example. But you can see that that is the graph of the sine of x. So it's another way that you can find that antiderivative using the slope fields. Now, let's construct a slope field for a slightly more complicated differential equation. And we're going to use the calculator to do this. So use a calculator to construct a slope field for the differential equation dy dx is equal to x plus y. And then sketch a graph of the particular solution that passes through the point 2, 0. So we plug all of that information into our calculator, and we use the calculator to construct this particular slope field. you can see that we also have graphed here in blue the particular solution that they were interested in. In other words, this is the point 2, comma, 0. And so that blue line is that particular solution. Again, you'll notice that what we've done is looked along those slope fields and, as best we could, drew a smooth curve that follows along a particular set. And that's what all of those would look like if we were to continue drawing that family of functions. The calculator certainly makes that a lot easier to graph. And let's look specifically at some of the points along this particular graph created by the calculator. For example, if we look at the line x plus y equals 0, or in other words, the line y equals negative x, we find that the slopes of that are equal to 0. And if we look along the line x plus y equals 1, that means the slopes are equal to 1. Because remember, it's dy dx equals x plus y. We're looking at the slopes. Now, the slopes get steeper over on this side as x gets larger. And the slopes also get steeper as y gets out, as y increases. Now, remember that blue line superimposed on here is the particular solution that we were looking for. So let's now examine another method for creating slope fields called Euler's method. In the example that we just did, we graphed the slope field and then found a smooth curve through that given point. Well, we could have gone the other way, which is that we could have approximated it by starting at a given point and then piecing together little segments to build a continuous approximation of the curve. And that's what's called Euler's method. So let's take a look. Euler's method for graphing a solution to an initial value problem. 1. Begin at the point x comma y specified by the initial condition. This point will be on the graph as required. Step 2. Use the differential equation to find the slope dy dx at that specific point. Step 3. Increase x by a small amount delta x. Increase y by a small amount delta y, where delta y is equal to dy dx times delta x. This defines a new point, x plus delta x, comma, y plus delta y, that lies along the linearization. Step 4. Using this new point, return to step 2. Repeating the process constructs the graph to the right of the initial point. And step 5, to construct the graph moving to the left from the initial point, repeat the process using negative values of delta x. Let's look at an example that will illustrate this method. And here we have our initial point of x comma y right here. And then what we do is we add a small amount to the x of delta x. We add a small amount delta y, which again is equal to dy dx times delta x. And that brings us to this new point of x plus delta x comma y plus delta y. And that becomes then our new starting point to repeat the process over and over. So let's take a look at an example where we can use Euler's method. So let's say that we have f be a function that satisfies the initial value problem dy dx is equal to x plus y, and f of 2 is equal to 0. Use Euler's method and increments of delta x is equal to 0.2 2/10 to approximate f of 3. To do this, we're going to set up a table, and we'll examine the table using the increments of delta x is equal to 2/10. So here we have our initial point where we're going to start, 2 comma 0. And we know that in this case, dy dx, which is x plus y, is equal to 2. Then we have an increment of delta x 0.2. Delta y, therefore, is 2 times 0.2, or in other words, 0.4. And therefore, the next point up, which is x plus delta x, comma, y plus delta y, is 2.2, comma, 0.4. So we continue that process, and really what I'm most interested in, of course, we're going to add each time an increment of 0.2, but the one we're most interested in is, of course, the final one. So let's take a look at that. We're at the point where we have our second to the last point here. We have our delta y delta x, our increment, our new value for delta y, and here is our new point. And so, using Euler's method leads us to an approximation for f of 3. In other words, x is equal to 3. F of 3 that's equal to 3.46496. Now, Euler's method underestimates a curve when it is concave up. Okay, so it underestimates it when it's concave up, and it overestimates a curve when it's concave down. The error in this particular example that we're looking at is actually about 16.6%, because the true value of f of 3 is 4.155. Now, using a graphing calculator and smaller increments, for example, use 100 increments of 1/100th, in other words, 0.01. And in that case, the estimate would be 4.1144, which yields an error of only about 1%. So you can see increasing those increments, or the number of increments, makes a big difference in how close your error would be. All right, that was a great lesson. In this particular section, we looked at differential equations, slope fields of those differential equations, and graphs of family of functions and particular solutions to those. We also took a look at Euler's method. Now, be sure to work those exercises that your teacher assigns, and we'll see you next time.